Good morning, everyone. I'd like to welcome you all to our fourth annual webinar on the risk-based community resilience planning. My name is Bruce Ellingwood, and I'm a professor of civil engineering at Colorado State University and the co-director of the center. We're very pleased that you could join us this morning. Today's presentations will focus on our theme for the fifth year of the center, the structure of INCOR for risk-informed decision making. As you will learn in this morning's webinar, INCOR is the computational environment that we are developing to implement the community resilience research that we've accomplished during the previous 4 years and to provide structure to our endeavors going forward. Before we move on to INCOR, let me just review very briefly, for those of you who have not attended a webinar before, what the center is all about. It's managed by Colorado State University. It consists of a little less than 100 faculty, postdoctoral scholars, graduate students, and actually some undergraduates as well, at a dozen universities around the United States. The research programs of the center are grouped into three broad thrusts. The first thrust deals with this multidisciplinary computational environment, INCOR, with supporting databases, which is the topic of today's webinar. The second deals with database management tools for community resilience assessment. And finally, the third major thrust deals with test beds, hindcast field studies, that provide the data necessary to further develop and support INCOR and validate it as a decision tool. Understanding community resilience requires an understanding of the functionality states of key physical, social, and economic systems within a community, as well as uncertainties that exists in the description of these states as functions of time. One of the features that distinguishes the NIST Center is its interdisciplinary focus on the entire process represented in this particular slide, starting with planning prior to the hazard event, continuing through an extended recovery period until the community is restored, perhaps to a new state of normalcy after some extended period of time. Our center, in its years of operation, has built its activities and its research, and I might say also the webinars that we've had previously around different stages identified in the curve in that slide that I just talked about. The center was formed in late February of 2015, and we are now a few months into year 5. In anticipation of our year 5 efforts, this morning's presentation will focus on the structure of the center's main work product, the INCOR computational environment for risk-informed decision making, which you will hear about from a number of the center investigators very shortly. To give you an overview of what INCOR is all about, we've accelerated in the past year our development of this platform and its system-level models and databases to provide the technology for understanding and enhancing community resilience. We're very excited about this development, and we hope that you will become excited about it as well as you hear what's been accomplished. INCOR will provide a unique set of science-based measurement tools supported by fully integrated databases and risk-informed decision models to optimize design and management of individual facilities and their interdependent physical, social, and economic systems. So what is it? It's an open source, or we envision it to be an open source research tool that integrates estimates of the impacts of natural disasters on the built environment and the associated impact on social and economic models that inform users as to the potential impact of such disasters on a community, the effect of various policy and project decisions that are aimed at enhancing resilience under various scenarios, and finally, the development of optimal strategies for enhancing community resilience through planning, recovery, and adaptation. Our vision is that it will be first and foremost a research tool, at least in the short term, to support NIST programmatic research on community resilience, to support collaborative research by others outside of NIST and indeed outside of the center in community resilience modeling and assessment, and finally will lead to the development of best practices for achieving community resilience. It's a very complex undertaking, and you'll hear more about this in the hour or so that follows. You get some sense of the capabilities and the complexities, by looking at this conceptual model of INCORE, starting at the left from a description of the community, description of the hazards, leading to, as you move from left to right, the impact of natural hazard scenarios on the physical, social, and economic institutions of the community, leading to an assessment of what the likely state of the community is following that event. And from there, one can examine various strategies for enhancing the resilience of the community, and optimally, or ultimately, determine a set of optimal policies moving forward that would be useful to community decisions makers, and would be useful in further informing research on community resilience and understanding it more completely. What you'll hear in the coming hour and a half, first of all, is a discussion of a more detailed discussion of INCORE. It's an overview of it and its scope, and that will be presented by my colleague and co-director, John Vandeland. You'll hear an extended description of the supporting algorithms that appear within those boxes on that flowchart. Damage to physical infrastructure from Jamie Paget, interdependencies and how they're modeled from Professor Paulo Gardoni, social impact from Walt Peacock, economic impact from Harvey Cutler, recovery modeling from Sarah Hamadeh, and community goals, metrics, and decision making by Charles Nicholson. Elena Sutley will talk about some of the supporting field studies and the validation exercises that we've undertaken in order to make sure that we have INCORE structured properly and that it can be validated. Dr. Jongsung Lee at our National Center for Supercomputing Applications at the University of Illinois will talk about the physical structure of the INCORE as a computational performance or computational evaluation package. And finally, I'll conclude with just a few remarks about our views on what the future looks like for INCORE as we're moving forward. So. This is going to be interactive to a degree. There will be a period of questioning and answering over the last half hour from about 11 to 11:30. You can send your questions to our monitors at the site indicated in blue, either during or just after the webinar. You can either direct your questions to a speaker, or the monitors will try to select the best respondent based on the topic of your question. You may also use the chat feature open in the webinar if that's more convenient for you. So with that brief introduction to the webinar this morning and what we hope to cover, I will introduce my colleague, John Vandeland, who is the center co-director, and he'll give an overview of the structure of INCORE as a risk-informed decision tool. John?
Thank you, Bruce. Good morning, everybody. As Bruce mentioned, I'll be running through the data and information flow in INCORE. As you saw from the initial flow chart, INCORE is a fairly complex modeling environment, and so I'm gonna break it down in sections, or what we call modules, and then you'll hear about the science from there. So INCORE is open source and flexible. Open source with core modules. There'll be a number of illustrative examples that you'll hear about, as well as the ability to start anywhere in the analysis. And so this means, as you'll see as we go through the flow chart, you can really plug in depending on what the event is at any point, using the script in Python that Jongsung Lee will talk about, using the tools. It can link to other platforms. Right now there is linkage to OpenSeas as well as EPA Net. So this is perhaps a slightly blown up version of the flowchart that you saw earlier. And so starting on the bottom left, I'm going to work in kind of fairly large chunks, try and work our way to the right here just with a summary. And so we start with the initial interdependent community description. And so essentially time t is 0. So that might be, you might time step in years if it's, you might do 5-year increments if it was a climate change or sea level rise problem. And so we start by describing the built environment. This involves things, building footprints, assigning archetypes, electrical power network, all the topology for these different networks, including water and gas, transportation, and then the connectivity, or what we call dependencies and interdependencies, and that's through an adjacency matrix right now, and other approaches are currently underway in year 5 of the center and on. The social systems, this involves census data, American Community Survey data, parcel data, and you'll hear more in detail. I'm not doing it justice, just mentioning 3. And then economic systems, looking at household income, labor, and wage data, and input information for firms as well as households, so looking at businesses and the households themselves. And then the infusion of money through federal relief and other mechanisms can be accounted for. So then we move from the interdependent description, we move to then the damage, what we would call the damage to physical infrastructure module. And so with this, it requires the hazard model as well as the damage models. There's 2 hazard tiers in INCOR right now. The tier 1 is executed completely within the environment itself, and then the tier 2 is run outside. So that could be, for example, if it was overland flow from surge, it would be an ADCIRC model, and then it's imported as a raster, I think a TIFF file, if I recall. So an example of a type 1 model in INCOR is the simulation of a synthetic hurricane. This would involve a past hurricane, but then we can move the track. It does take into account ground friction when it comes ashore, and then changes the wind field accordingly. And I should add, there is a database of past hurricanes. It's not extensive yet, but it'll be built on as the data is procured. A tier 2 example would be something like ADCIRC, looking at water levels and wind vectors combined. And so there's a complete hindcast available, and that'll be released with INCOR at the end of the year, as Bruce mentioned, or will mention, excuse me. And that'll be for Hurricane Ike. There'll probably be several others as well. Another example, a quite advanced example from UIUC, is a 3D model of a fault rupture, in this case, the December 16, 1811 New Madrid earthquake. And that involves 7 million elements, so a massive finite element model of this rupture. And this is particularly advantageous when there's a complex soil structure, such as in the Memphis metropolitan statistical area, which will be another example provided. For the damage models themselves, we then would have either a GIS data file, a GIS file, or simply a raster file, and with the building locations, with all of the topology, and then layers with their attributes, things like the damage fragilities. And so here we see, an example of damage fragilities for flood. And then the interdependency description amongst all these things. And that also ties the dependencies and interdependencies of the socioeconomics as well. So then from damage, we move into the functionality module. Now the focus is on all functionality, but in this case, until we get to the socioeconomic systems in a moment, the functionality described here is the physical systems that support the socioeconomic infrastructure. So this is things like water and power networks, transportation, the buildings themselves, and these are models that describe either they are functional, they're not functional, or how functional, and then are updated as we circle through the analysis in time, either by month, it could be by quarter, it could be by year, it could be by decade if you're looking at something with a 100, 200 year planning horizon. And so from functionality, we then move down to our socioeconomics modules. That's the CGE, which is the computable general equilibrium model, an economics model. that predicts changes in household income, employment rate, earnings by sector. And one of the key features of this is, and you'll hear more about that in the science portion of the webinar, supporting science portion, is that it's a spatial CGE model, and that allows it to, in these larger communities, it allows it to actually tie together with the physical infrastructure, because the physical infrastructure has a topology and is very spatial. And then stochastic population allocation, which allows us to take census data and take it down to the household level, so that we can then do the analysis at the household level where the socio-demographics are at play. And this leads directly into our population dislocation analyses, business disruption and recovery, and really all the linkages between work, school, and home. So we then move, at that point, then we would have a state of the recovery at one point in time. And so this could be immediately following the event. And so you recall from Bruce's presentation earlier, the 5 points. And so this would be at point 2, just after the event. And so then we increment time, and again, time is not, if you're thinking dynamics, if you're an engineer, it's not by seconds or split seconds. It can be years, it can be months. And we increment this and we go around. And so we're then updating the functionality, and as the physical infrastructure, as the socioeconomic institutions, the social institutions are coming back online, and this is all interacting. The key then at that point is, once we have essentially a solution, how long it took to come back, and I'll explain how we measure that here. So we have a prescribed number of solutions that we're looking for, and so these are near optimal solutions, and you'll hear about that in quite a bit of detail here in just a little bit in the supporting science portion. But the idea is that these are subject to achieving the community goals based on stability areas, and those are population, economics, services, and then also physical services. So if enough optimal or near optimal solutions or acceptable solutions aren't achieved, then we continue on. And so for that, we'll look at more the top left portion of the flow chart. And so what we would do is, first we would determine, is optimization still possible, or are these algorithms? Now remember, this is a huge model of a community. It involves socioeconomics, it involves physical infrastructure of 5-6 different types. Every building is modeled, and we can model them in chunks, in clusters, we can model them individually. And so this is all interacting. And so it may be that when we get there, we look at it and we say, well, is optimization still possible? And the reason it might not be possible is because the community goals have to be met based on those stability metrics I mentioned. But it's also subject to economic, social, and physical constraints. There's only certain things that can be done or acceptable to each community individually. And so it may not be possible. And if it's not, then we adjust the community resilience goals or the constraints. We relax constraints, and then we restart the analysis. If it is still possible, then we move up to the top left. And so there's a large suite, presumably large suite of policy levers and decision combinations, which we call PD. And from those, that's what we're optimizing across essentially within the analysis. So we're selecting those combinations. And so they can be combinations of physical, social, economic, can be all sorts of things. It can be simply raising the base, the first floor elevation above the base flood elevation level. But it could be that combined with relaxing some kind of permitting, or it can be all sorts of things. And so we would then be searching across those, and so then we would restart the analysis, and once we make changes, we re-describe it's no longer initial, but we re-describe that community description by changing the physical, social, and economics models, the damage models, the functionality, and we go back all the way through the analysis, and we're incrementing K, and K is a new policy. But again, remember, looking at that far right of this, we stop when we have enough. If we said, okay, we want 20 policy combinations to consider at the decision maker level. So with that, again, you'll get a better feel for that. That was fairly quick, but you'll get a better feel for that shortly, I hope, when we get to the science behind INCOR coming up in just a moment. But how does INCOR differ from existing platforms? There's a lot of good platforms out there. Well, the key with INCOR is that it's the integration of advanced engineering, social science, and economics models. And so it allows us to constrain a policy or define policies in that kind of tri-space, if you will, of physical, social, and econ. And it's not really a software. I think I've called it a software, maybe even up here, but it's really a work environment. If you think of a MATLAB or you think of these types of environments, you'll be able to pull your own script, pull existing script and modify it and see what those changes do. It's an open source platform, as Bruce mentioned a few minutes ago, and anyone in the world will have the ability to contribute to the core, provided that the verification and validation requirements are met. But again, anyone would be able to use that either on their PC or online. And then the ability to use existing community level examples. There'll be at least 3. So pulling in a simple change in a model and spreading that out throughout an existing community that's already in INCOR to see what change your model has. What change that makes on the resilience and the recovery of a community. And then finally, the ability to measure community resilience. In other words, measurement science. And so we have to be able to measure it to be able to move it forward. And also to be able to define your own metrics. And so with that, I'd like to invite Dr. Jamie Paget from Rice University up to start the Science Behind INCOR presentation series. Jamie.
Thank you, John, and good morning. I'm very pleased to represent the group to share some of the ongoing work to develop some of the science behind INCOR, specifically with looking at damage to physical infrastructure. Behind the scenes within INCOR are a series of different modules that help us to predict the physical damage to components of infrastructure systems, and then look at their performance across distributed infrastructure networks. One of those key components that we leverage would be fragility models, which are highlighted on this slide. And they help us to depict the likelihood of damage to these components given intensity measures of hazard events or other characteristics of the structure or infrastructure system. What I'm illustrating on the slide here is the flexibility or ability within INCOR to ingest a range of different types or functional forms of fragility models. You see on the left-hand side the classic example of a two-dimensional fragility curve characterized by a cumulative distribution function, or we have the potential to ingest custom expressions that offer estimates of the likelihood of damage or limit state exceedance given perhaps a vector of intensity measures or a set of characteristics of the structure or system. Currently within INCOR, we have on the order of 12,500 fragility models that are ingested within this platform to help us in assessing physical infrastructure performance. There are a couple of reasons motivating this large set of fragility models. One is that we are leveraging both existing fragility functions from the literature and also ingesting the wealth of fragility functions that have been derived as a part of the COE effort over the last several years. The second is that we're addressing a broad range of different infrastructure systems when subjected to multiple hazards. For example, we're looking at building infrastructure, at power, water, telecommunications, and transportation infrastructure, and each of those systems with their constituent components with a few examples listed on the slides. We're also looking at predicting performance under a range of different hazard events. For example, seismic damage, flooding from coastal surge and wave, wind-induced damage, tornadoes, tsunamis, including a range of combinations of some of these hazards, as you saw earlier, for example, the coupled wind surge and wave effects. Just to show you a quick sampling of some of the types of models that are used to predict physical infrastructure performance. For example, within the building world, looking at a range of different structural systems under various hazards, and you see examples here from some of the INCOR researchers' work looking at steel or concrete buildings under seismic damage or under tsunami loads. But what I wanted to emphasize here is you see the transition in different potential functional forms from fragility curves to fragility surfaces and the range of different types of systems addressed. Within the transportation infrastructure world, we're addressing two key modes of transportation, primarily looking at bridge and roadway networks as well as railway networks. And some examples on the slide from those systems here of the constituent components of those systems. And lastly, when looking at our other infrastructure systems, for example, power and water system, we have a range of different constituent components of those infrastructures. And a few examples are shown here, but what I wanted to highlight is the ability of INCOR to adopt time-dependent fragility functions that allow us to capture the effects of aging and deterioration on these infrastructure assets throughout their lifetime when looking at hazard performance. All of these component vulnerability or fragility models are incorporated into network level models to look at regional scale performance metrics across these infrastructure systems. And a graphic example is shown here of looking at the basic idea that's conducted across a range of infrastructure is that we depict a graphical and mathematical model of that infrastructure system. We have characteristics associated with that system in terms of its capacity or its functionality and associated physical assets and vulnerability models for those constituent components. We assess pre-event performance as well as post-event performance of that infrastructure, leveraging, for example, some of those fragility functions for looking at damage of key components, and then assessing how that functionality evolves in time after the event. With these mathematical depictions of our infrastructure systems, we conduct either connectivity-based or flow-based analyses to look at various infrastructure performance metrics. On the connectivity side, this may be things like looking at the probability of connectivity to key services or to key nodes within our infrastructure network, looking at various metrics like operational path ratios, or we may look at flow-based measures, for example, travel time through a transportation system. I want to show you a very brief example of how some of these models are integrated within the framework, leveraging some of the ongoing work from one of our center test beds, which is in the Galveston area along the Texas coast. You see here an image of Galveston Island and the transportation system along the island as well as connecting the island to the mainland. You also see a set of building inventory. This specifically is looking at residential construction for single and multifamily housing. So about 16,000 parcels and roughly 21 bridge structures and the roadway network connecting those to emergency services and medical facilities. The image here is showing the mapping of each of those parcels for looking at vulnerability modeling of our building infrastructure. We leverage those INCOR fragility functions when coupled with hazard simulations to assess the likelihood of damage to those structures. For this particular example, the predictors that are employed include things like significant wave height, freeboard for the house, and characteristics of the structure like the age of the house. For the transportation system, we're looking at components such as bridges and roadways, considering the unseating potential of bridges when subjected to surge and wave, or looking at the washout of coastal roads when exposed to surge and flood events. The first set of results that I want to highlight here are just showing you the idea or the types of visualization that can be portrayed to illustrate individual component level damage, and then I'll show some integration at the network level. On the left-hand side, we're looking at that building inventory, parcel level prediction of damage to some of that residential construction, looking at the spatial distribution, color coding by increasing failure probability as we move from green to red. We can look at different scenario storm events, which are shown here referred to as a routine or a design level event, or probabilistic hazard simulations. On the right-hand side, we're looking at the components of the transportation infrastructure, looking at segments of roadways, or at individual bridges and their potential for damage. As we move to the last set of examples, we transition to that network level performance assessment. On the left-hand side, we're looking at connectivity-based performance measures, where we're integrating the potential for damage to households and what is the likelihood of being able to reach those damaged structures from key emergency services like fire stations. As we move to the right, we start to transition to flow-based measures. What would actually be the travel time to reach those locations or clusters of damaged buildings from critical facilities? These types of models serve some of the building blocks for the interdependency modeling that you'll hear about next. And I'm happy to pass the ball to Professor Paolo Gardoni from the University of Illinois.
Thank you, Jamie. Thank you. So in this portion of the presentation, I will talk about the modeling of interdependencies among physical infrastructure and social systems, and I will explain why it is important to model such integration and how this can be done in a mathematically rigorous way. Communities are composed by multiple layers of structures and infrastructure. We can have buildings, transportation network, electric power network, water network, just to mention a few. The functionality of infrastructure depends not only on the physical damage to the individual components, but also on their connectivity. And the connectivity of the individual elements in the network capture the network topology, which can be described using an adjacency matrix. What I'm showing here as an example is the adjacency matrix for the example network, where 1 indicates that there is a direct link between two elements and a 0 indicates there is no such a direct link. For a given region of interest, we also need to define the footprint of each network. The footprint of each network might exceed the footprint of the region of interest. Different networks might have different footprints. And in general, the definition of each network depends on 4 key factors: the type of information of interest, whether it's physical damage or loss of functionality, the existence of easily recognizable physical boundaries and the possibility to model such boundary conditions, the existence and location of strategic elements that need to be included, like generation nodes, and the need for modeling the damage propagation among infrastructure systems. To illustrate some of the concepts presented today, I will use the city of Seaside, Oregon. As part of the work of the NIST-funded Center for Risk-Based Community and Resilience Planning, we consider a number of test beds that allow us to test and verify different algorithms through calculations, experience, and intuition. One of the test beds is Seaside, Oregon, that has a population that fluctuates between 6,000 and 14,000 people. They could be subject to earthquake scenarios originated from the Cascadia subduction zone. So for Seaside, we define the water network at the city level because it's a self-sufficient system. The transportation network is modeled at the county level and then extended to include the larger city of Portland. And the electric power network is modeled at the state level in order to be able to run a power flow analysis. Once we define the footprint of a network, we then need to define its granularity, or if you want, the resolution of the model. So we define a tributary area as the area served by a single network node, and then by changing the tributary area, we can define networks with different levels of granularity. And in the limit, the most refined model considers each single parcel or house lot as a tributary area. The nodal value of the quantity of interest is then the spatial average over the tributary area. In terms of modeling, different granularities affect our ability to describe the spatial variability of the impact over the area of interest, and I'll say more about this in the next slide. affect our ability to describe the changes in the network capacities and demands following a disrupting event, and affect our ability to describe the recovery process, since skeletonized networks only include the main distribution line and not the smaller distribution lines. It is important to capture the spatial variability of the impact over the area of interest, because certain population groups might be more impacted than others or recover more slowly, and tributary areas that are too large would underestimate the actual societal impact. So the detailed network allows us to capture the variability within the larger tributary area used for the skeletonized networks. Infrastructure often depend on each other, and such dependencies might indirectly affect a network functionality. Buildings, for example, need the service provided by the water and power networks. The water network depends on the power network because it needs power at the pumping station and control systems. As a result, even if a network has no physical damage, there could be a loss or reduction of functionality of such network because of the physical damage and the corresponding loss of functionality of a supporting network. So we need to translate the physical damage into a loss or reduction in functionality, and then propagate such reduction across all dependent networks. The dependencies or interdependencies among networks can be represented by using an expanded adjacency matrix. What I'm showing here is the expanded adjacency matrix for network A and B. The top left sum matrix is the adjacency matrix for network A. The bottom right sum matrix is the adjacency matrix for network B, and the two off-diagonal sum matrices capture the dependencies of A on B and B on A. For example, considering the water network, the expanded adjacency matrix can be used to model the change in the capacity of the water network due to both the direct damage to the water network as well as the damage to the supporting electric power network. But not only the capacity, also the demand can be affected by dependencies. In particular, the dependencies of infrastructure on social systems. For example, building damage can lead to population dislocation that affects the post-event water network demand. So the updated network capacity and demand can then be used in a flow-based network analysis to assess the functionality and reliability of the network. As the individual components recover, the network functionality also recovers. And the dependencies, interdependencies between physical infrastructure and social systems also shape the recovery process. Lack of potable water for an extended period of time could induce further population dislocation. And the additional population dislocation could then affect the network demand over time in an iterative process that captures the interdependency between physical infrastructure and social systems. Considering the example of Seaside, we studied the effects on the water demand of population dislocation due to an hypothetical seismic event. Population dislocation is estimated using a logistic model based on the probability mass function of the residential structural damage and other socioeconomic factors like income and race. So external population dislocation results in a decrease in the water demand at the node of the water network. And the assessed physical damage of the water network and the reduced demand due to population dislocation can then be used in a water flow analysis to see if the new water demand is met. We then looked at the recovery of the water network, and a flow analysis of the recovering network with the reduced water demand due to population dislocation allow us to assess the availability of water at each node over time. And we can see that immediately after the considered earthquake, the damaged network is largely unable to satisfy the minimum pressure requirement. However, after about 84 equivalent hours of repair work, we have a significant improvement. The dependencies between physical infrastructure and social systems also shape the recovery process. This is the recovery process that considers only the initial population dislocation due to building damage. However, not having water after, for example, 72 hours might lead to an additional population dislocation, now due to lack of water. Because of the additional population dislocation, the recovering water network is now able to meet the new demand in less time. So in this portion of the webinar, we saw why it is important to model the integration of physical infrastructure and social systems. We saw how this can be done in a mathematically rigorous way. Also, using 100-center testbeds, we saw that neglecting the interdependencies between physical infrastructure and social systems may lead in overestimating the demands on the physical infrastructure, in underestimating the recovery time of the service provided by the physical infrastructure, and in underestimating the impacts on the society in terms of, for example, population dislocation. We also saw that it's important to select the proper model granularity, since certain population groups might be more impacted than others or recover more slowly. A model that are too coarse would underestimate the actual societal impact. While today's presentation focused primarily on the modeling of the interdependencies between physical infrastructure and social systems, we're also developing models for the interdependencies with economic systems. Ultimately, INCORE will model interdependencies within and between critical infrastructure, social institutions, and economic systems for an optimal risk-informed decision. This concludes this presentation on the modeling of interdependencies. Our next speaker is Professor Walt Peacock. Dr. Peacock is a professor of urban planning in the Department of Landscape Architecture and Urban Planning at Texas A&M University.
Thank you, Paolo. So I'm going to actually pick up on a number of points that Paolo was talking about, as well as Jamie, and that is these interdependencies between linking together engineering and our social science modeling. So I'm delighted to be able to come up here and talk about these issues. To do that, I'm going to kind of give you a little bit of a history of the evolution, if you will, of our social modeling within INCORE, and focus a bit on losses, mostly on population dislocation, although the types of things I'm talking about will also have implications for the recovery-related issues as well, too. So our social science modeling is based on and draws from a long-standing social science research that shows that disasters are not equal opportunity events. They do not impact populations or the variety of different populations in our communities evenly or equally. Social, economic, historical, cultural, and demographic factors shape the nature of our communities. If we think of housing can be quite heterogeneous in our communities, not only in terms of age and those issues, but also in quality, in the types, as well as how households and individuals are related through rental or ownership as well, too. Access to housing is shaped by these broad social, economic, and historical consequences. If we look at our communities in terms of neighborhoods, we all have heard the right side of the tracks, the wrong side of the tracks, the good side of town, the bad side of town. And if you talk to a realtor, what do they say? Location, location, location. Our neighborhoods, our communities are not homogeneous in any respect in that way. Rather, they're quite heterogeneous. We see different populations located in different parts of the communities, and those things have consequences for hazard exposure, for infrastructure, for maintenance of infrastructure, for the quality of that infrastructure, as well as other issues with respect to resources and opportunities. Indeed, Arthur Stitchcomb, a famous economic sociologist, talks about neighborhoods as neighborhoods of fate that shape our life chances, that shape our opportunities, if you will. And in the context of hazards, in the context of disasters, they have major consequences as well. In the social science parlance, basically we oftentimes kind of talk about these issues in terms of social vulnerability. So what are the broader socioeconomic forces that shape access to those resources? So factors like race and ethnicity, gender, education, income, wealth, age, et cetera, have major consequences for capacities of households, access to information, the ability to act on that information in terms of power and control, as well as resources to mobilize also. It's a consequence of all those factors that shape, indeed, our ability, our household's ability to act with respect to warning, to be able to address the potentials for damage, and then ultimately the long-term recovery kinds of issues as well too. So these broader factors shape the outcomes often of these disasters. Indeed, we can oftentimes talk about a lens of social vulnerability. If you think about the initial states in our communities in terms of these heterogeneities, or much more importantly in terms of inequities or inequalities, those can often be exacerbated after an event in terms of disaster. The disaster consequences are not equally felt out there. And then in terms of that long-term recovery process as well. So we can look at that lens shaping and the nature of those recovery processes. So whether we're talking about damage, housing loss, dislocation, shelter needs, family and household disruption, and even psychological consequences as well in terms of children and PTSD kinds of issues. Based on that, in our kind of initial work, is to simply develop kind of social vulnerability maps. Or if you if you talk about different kinds of, utilizing different kinds of census data to be able to map out the community in terms of poverty, in terms of gender and household structure, in terms of where concentrations of younger children are, elders in poverty, access to transportation, tenure, poverty, et cetera, et cetera. Those, in turn, can be collapsed together to actually kind of capture different, what we call second-order social vulnerabilities, and then ultimately third-order as well, too. Now, in a planning environment, these are critically important to help identify what's going on. But in addition, we can take the engineering modeling and then map that out in terms of differentiation, in terms of disaster, in terms of those impacts, and look at different communities to better understand where it is we're going to have particular problems and particular issues. That then is kind of like the first step of our process, and what we have done then is take those and create fairly simple beginning-wise dislocation models. For example, using HAZUS, which basically focuses on damage to single-family and multi-family structures. Based on that, then predicts dislocation. We've then elaborated on those by developing much more broader empirical models that include damage, include characteristics of the population in those areas, including income, including race and ethnicity, to actually map out then where we're going to see higher levels of dislocation given a particular event. This is for the Shelby County area. The darker red are where we're experiencing higher levels of household and individual dislocation as well too. That work, though, is basically pass-through, i.e. we take the engineering damage information, apply that or bring that into our social science models, and then predict then these particular dislocations or particular impacts. The engineering model is high resolution at building level, as Jamie has already talked about, with the fragilities there, as well as Paulo has talked about in terms of infrastructure. With our social science issues, the initial models are that way as well, too. That is, looking at individuals and looking at households. But often we don't have those data. As a consequence, we use census data to do that. I've kind of tried to characterize that here. The two yellow areas are census block groups, spatial areas. We've got a random kind of distribution of households within those areas. And basically what we do is we use aggregate level data from those census, from that census data, plug those into our models to help us capture what's going on. Engineering comes in, we use then the census level models to actually predict what's happening. What we're doing in NCORE, though, is actually dramatically changing the nature of that through the creation of population inventory data, linking together then census data, linking together parcel and other administrative data, linking it with the building inventory data, the data that's utilized to actually understand better what's the likely fragilities, as well as critical infrastructure data. We're taking that population inventory data, generating then generating data on particular households and distributing those to housing units within the communities, using parcel data to help us filter out non-residential data, using census block data to provide counts, to provide better understandings and linkages between social characteristics and building types, and then adding ACS or American Community Survey data to provide more specific kinds of issues. So you can see from this map then we've got households, those are the little green dots there, in housing units, single family, multifamily, and not in commercial areas, not in areas, so we get some much finer resolution, able to kind of map out the hazards in those areas. We can develop from those much more refined social vulnerability maps where we've got multiple characteristics that we are looking at hotspots. These are minority renters in the communities. This is in the Galveston test bed. But finally, and most importantly, we now have households with household characteristics linked with the engineering models, and that link is the housing unit. The housing unit in different kinds of residential structures, and then linked to that is the infrastructure as well, too. So we're able to integrate, much as Carla was talking about, integrate social science and engineering with respect to our modeling. And we can take the individual and household level modeling from our social science data and directly link that in as well, too. So high resolution social science data combined with high resolution engineering data, that it creates a computational environment where we can link these interdependencies together. So I hope that gives you a little bit of a sense about what we've got going on. And now I'm going to turn it over to Harvey Cutler, who's a professor of economics here, to talk about economic modeling.
Yes, so this is comprised, the work is comprised of a number of faculty members at the Department of Economics at CSU and a large number of graduate students. So just wanted to point that out. So our objective was to integrate civil engineering modeling, social science modeling, and economic modeling into one general model. So that's what we were trying to understand how engineers talk, and social scientists we had a better idea, but I realized that civil engineers and economists actually have a lot in common. So when you have a damage, a natural disaster, it impacts buildings, transportation networks, electricity, and water. And also, it impacts the social fabric of the community, and as well as economic outcomes. So what we want to do is build a model to capture all these linkages. So what we first had to do was look for data. We've been playing with economic data for quite a while, but we also had to broaden our data collection to encompass civil engineering requirements and also social science. So we had a meeting, I think, 3 or 4 months after we got the grant, and Walt and Nathaniel came up, and they helped us put together the data set. And the one that they really helped us, this was his loads data, the 5th one. So, and that data is where people live and where people work, which was an important aspect of building our spatial model. So we organized all this data, which is publicly available, and then started to build our models. So, and we initially played with a lot of this data before, but we included hazards, loads, and some of the American Community Survey we had not looked at before, but now we're using. So what we did is we built 3 CG models, or computer general equilibrium models. We built one for Centerville, and this was the trial run to understand how damage that are calculated by the civil engineering team, primarily to capital stock, how that's integrated into an economic model. So we used Centerville as our test piece to develop all the linkages, or some of the linkages between civil engineering and economics. So we worked on that, and then after that, then we built our Joplin model, which then examined the 2011 tornado. And what we did with that was we did hindcasting. We forecasted using our 2010 model what the impact of the tornado would have been in 11 and 12, and so we spent quite a bit of time with that. And then our third model that we built was the Shelby County model, and this was the highly spatialized model we did. And just to emphasize or point that out, Shelby County is divided up into 8 Puma regions. The Puma regions is not critical, but most of the economic activity appears in sectors A and H. And so what we have is we have work centers in each of these 8 regions, and we also have people living in all 8 regions. So we have people living in D and working in A, or living in E and working in A. So we have all this labor commuting going on between these different regions. And so if there's damage to A in terms of a natural disaster, or in this case an earthquake, that does have reverberation effects all over the county. And we also have trade, intermediate input trade across all these regions. So this is probably the most spatialized model we've ever built, and it's actually pretty complicated. We're still understanding, just from an economic perspective, the linkages, let alone just the damages caused by a natural hazard. The computal general equilibrium model is broken up into 3 general categories. We have firms that maximize profits when they make their decisions, and they employ labor, and they also employ capital. And capital is the one that's damaged when we have a natural disaster, or that's one of the aspects of damage. So we have these firms that are located in all 8 regions in Shelby County. And we also have 5 household groups per Puma region, and that's delineated by annual income. We will be breaking it up into ethnicity groups, and we could do, the data is specific enough to break it up in different groupings. And so we have households, when they make decisions, they're making it and depending upon them maximizing their own welfare. And then we also have a government, in this case it's a local government, and they collect tax revenue, and with that tax revenue they provide government services. And so what we're interested in is when the shock occurs, how does the behavior of all these components interact? And here's the picture. I will tell you that I borrowed most of these slides from one of my PhD students, Yu Chen, who's much better at making slides than I am. So this really captures the integration between civil engineering, economics, and social science. We have the natural hazard up top, and that could impact the quality of buildings, the supply of water and electricity, and what that ultimately impacts is the functionality of the building. And the civil engineers have been able to develop functionality at 5 different levels, and we've been accommodating that. So if the natural hazard impacts building functionality, it then reduces the capital stock. And if capital is reduced, productive capabilities in the community fall. And also demand for labor will fall. There is some substitution, but the general effect, the direct effects is employment will fall. And so then we could look at losses in household income, and also the trade between the different of the 8 regions, let's say in Shelby County. Now, what we borrow and getting from Walt's group is migration, because different hazards impact migration of households moving in or out of town dependent upon a natural disaster. So all the work that Walt is doing informs us about the elasticities that we want to use to govern when a disaster occurs, how many households will migrate out of town. So, and then we also have damages to transportation networks, and we've been working on that. We still have a lot more work to do. And that can impact getting to work. It could be impact shopping. And so that also reverberates in different types of economic outcomes. So that's just a general picture. We also had to build an open source program, which was probably the hardest thing I've ever been involved with. So we have GAMS, which is a proprietary program. We had to develop an open source program, and we've made a lot of progress. We're just about done. Shelby County is about 99% done. I think there's a parentheses out of place. We just can't find it, but we're looking. So, oops, one more. So, what we're figuring out to do is in NCORE is we're trying to automate the creation of a CG model, is to actually have different modules to download this data automatically. So, and we actually have the mechanism about 80% done just in our world, but then we have to integrate it into NCORE, and that will be Zhang's problem, but that's not ours. But that's been a real challenge. So I'd like to now introduce Sarah Hamaday from Iowa State University, who will be talking about recovery. Thank you.
Thank you, Harvey. I'm going to talk about some of the ongoing recovery modeling efforts from multiple different groups in the center in the past few years, and some of it, as I said, are ongoing. So just to give a very quick recap or summary of these types of models, I'm going to talk about some housing recovery models where we are trying to find the factors at different levels from different data sources that can determine the trajectories and success versus failure of housing recovery outcomes. Business recovery modeling, the work that has been done for businesses. There has been so much work done on functionality restoration with different functionality states through Markov chain modeling. Infrastructure and transportation, which Jamie and Paulo talked about, and economic recovery models that Harvey just talked about. What I will spend my few minutes here on is going to be on talking about some examples of housing recovery models and then business recovery models to show how things look like so far. So with the housing recovery models, Walt did a very good job setting up the stage that talking about what informs our modeling, our high-resolution housing recovery modeling. The very, very important tenet behind all of that is we look at housing recovery as a long-term, as an unequal, and a very complex process. So based on that understanding, some of the major goals that we have been following for our modeling work is number one, to adapt more complex, multidimensional, and interdisciplinary ways to measure housing recovery, and then looking at the relationships between those measurements. And then ultimately finding the explanatory factors that can help us understand what shapes the outcomes when we measure outcomes in a number of different ways. So a few ways to think about the measurement problem when it comes to high-resolution housing recovery modeling. The only ones that I'm going to focus on today are going to be number 2, number 3, and number 5, the success versus failure. The important thing I want to mention before we show any examples is that different models that I'm going to show are built, some of them are built based on completely publicly available and secondary data. Some of them are using primary data through our survey work in different places. So restoration as success versus failure. Very high resolution model. This model was built after Hurricane Ike 2008 in Galveston Island, Texas, looking at trajectories or the percentage, the amount of assessment value that has been restored or not in any given year. And here we have 7 years after the initial impact of Hurricane Ike. Now, we were able to build a causal model, a logit model, that was going to predict for us the odds of success, the odds of restoration of housing value in any given number of years. The very basic components we were looking at were, of course, damage at housing unit level, tenure status, income, minority population. Just to show you an example of the outcomes of that high-resolution housing recovery model. Here we can see the probabilities or odds of restoration changing based upon, of course, a number of years that are passing after the hurricane. The damage states, from damage state 1, which is minor, all the way to damage state 4, which is the most extensive damage, and comparing different tenure status, rental occupied versus owner occupied. We can easily see from this prediction the years, the number of years after the initial impact of the hurricane, where the probabilities are somewhat stagnating for certain tenure status and certain damage states, and then the differences between damage states versus tenure. Now, the other thing that we were able to do through our own primary longitudinal data collection in a field study, I'm using Lumberton data here. We have done 4 waves so far, and I'm using some of the wave 2 data to show some examples. Now, what was really interesting here was that we were able to come up with more complex, more multidimensional ways of measuring housing recovery, to build models that would compare what factors lead to success versus failure when we define success versus failure in a number of different ways. So I'm going to show 2 models that look at outcome as repairs being completed, how long it takes for the repairs to be completed, and the occupancy. Does the occupancy happen or not? How long does it take for the occupancy to happen or not? Now, another quick thing I must add here is that we were able to design a household survey from wave 1, which was used like 2 months after, that was wave 1 data collection, 2 months after Hurricane Matthew in Lumberton, North Carolina, asking questions from households, not only about their damages, about their life disruption, dislocation, but also about access to resources and their decisions versus about whether they want to stay, they want to leave, so on and so forth. So we were able to collect at household level so many explanatory factors and a number of ways to measure outcomes. Now, using that data to build some causal models. First, looking at just completion of repairs, success versus failure. This is wave 2 data after 14 months. What were the factors that could explain that success versus failure? Now, the types of variables I'm using here are level of damage, access to resources, different types of resources, minority status from a race or ethnicity perspective, and income level of the households. And you can see clearly the most significant explanatory factors that come up. We have, as an example of predictions from that model, we have the damage levels, we have the minority status, and we have this factor of not only you had insurance or not, but did you receive a payout from your insurance 14 months after the event, which you can see determines the outcomes. Now, looking at an outcome from a different way, still repairs completion, but the length of time. We want to see what factors can explain that length of time for completion of repairs. And again, major impact from minority status, major impact from whether or not folks had received insurance payout, and then income level, definitely. Now, another way that we had from this primary data collection to model housing recovery was the occupancy. It was very interesting here to see how the minority status did not come up as a very significant factor in explaining whether or not the occupancy happens and how long it takes, which I think is a very interesting thing to look at when we talk about how long it takes to finish repairs versus how long it takes for folks to come back to the houses. We knew, we had this hypothesis that for minority folks, they wouldn't wait for the repairs to be completely finished to come and occupy houses. Now, I want to move on and also show some examples of the business recovery models that our teams have been working on. This shows some of the processes that have been undertaken to build these models, going through literature review, identifying some of the most significant factors. The factors that are involved are the ones that are available through secondary data. And then we have, so far, 3 field studies that have been used to build models. Now, what the business recovery team has been able to do is using our Hurricane Ike, Hurricane Matthew, now Hurricane Florence business recovery data to build models that do get updated with this Bayesian approach, do get updated every time there is new wave of a field study, every time there is a new wave of a survey work. And with this Bayesian approach, what they have been able to do is to update, calibrate, and improve their disaster recovery models. Maria Watson is here. If anybody had any questions about details of these business recovery models, I'm sure she'll be able to give us more details. With that, I am going to pass the ball to Charles Nicholson from Oklahoma University.
Thank you, Sarah. If we look back at the in-core flow chart, we can note that this portion of the diagram depicts the in-core functionality to enable a community to analyze and understand its current resilience status. Whereas this upper portion focuses on how a community can identify and analyze its desired resilience status, and additionally, what it needs to do to understand and obtain those goals. In-core is meant to match community resilience goals to risk-informed performance criteria. These goals should be based upon the social and economic needs of the community. However, identifying and understanding realistic goals can be challenging. To this end, the modeling environment will facilitate exploration of both resource-constrained goals and aspirational goals, which may not be currently feasible. Valid constraints may include economic or political constraints, labor shortages during recovery, or many others. If a community's resources are insufficient to meet its aspirational goals, the tool can be used to explore possible strategies of how best to fill that gap. INCORE also supports sufficient granularity for goal setting and impact analysis on subpopulations, including often overlooked socio-demographic groups. INCORE facilitates trade-off analysis with respect to conflicting goals competing for the same limited resources, whether this relates to short-term versus a long-term outlook, or mitigation interventions focused on residential structures to reduce population dislocation versus investments on commercial and industrial buildings to reduce direct economic loss, or many other possibilities. The Center will soon emphasize new work on addressing systemic issues such as centralized versus decentralized decision-making by different actors within the community and the value associated with coordinating those efforts. We have implemented risk assessments of solution approaches and are continuing to extend this through a variety of methods to support the stochastic nature of the problem space, including various sensitivity analyses or probabilistic goal setting. That is, for example, we want to be able to say that we're 95% confident that a given solution will meet an objective or a constraint. This is an important feature in order to be able to tie the uncertainty propagation through into quality decision support. Ultimately, the research objective is to establish and further the science of resilience. The tool enables one to determine rigorous, quantifiable, and specific objectives that can be tracked and measured through time. Taking a look at an example goal, which has been adapted from the NIST Community Resilience Planning Guide, we can consider the population stability metric, the percent of people that are in their pre-event homes at a given time at a specific location or within a subgroup of the actual community itself. Under current state of the community, resources and plans that exist, INCORE may report that the percent of people in their pre-event homes does not reach 90% until 6 months after a disaster occurs. With this information, a community leader or researcher may determine that the goal should be 90% in their pre-event homes by week 6. Considering all the possibilities, there may be many pathways in order to be able to reduce this time gap. We could, for example, reduce the initial population dislocation through pre-event mitigation interventions such as building retrofits, or we could focus on increasing the reoccupancy rates after the disaster by reducing the repair times for the infrastructure itself. The optimization element within INCORE has been and continues to be designed in such a way to be able to tie together the various models developed in the center. From the discrete state continuous time Markov chain models for building recovery, to population dislocation and reoccupancy models, to the computable general equilibrium models from the economics team in order to be able to measure economic health. By connecting the decision support to these state-of-the-art models, we can address a wide variety of problem types and explore a suite of policy levers to obtain goals. We seek to ensure that INCORE is developed with a breadth of policy options. That is, actions that communities can engage in, from direct physical infrastructure interventions to non-structural approaches, including economic incentives or land use policies. Depending on the community and scenario context, multiple policies may be effective. The best solutions may entail a mix of several feasible policies. I refer to this mix as a policy strategy. And multiple strategies may be effective. Ideally, we can provide an optimal policy strategy to enhance resilience. That said, while optimization is desirable, we realize that it may be impractical from a mathematical perspective and from a time perspective. So therefore, we're using an array of traditional optimization techniques as well as modern meta-heuristics to search for near-optimal or high-quality solutions. We're also planning on adding rigorous approximation approaches to the platform in the future. Nevertheless, we aim to provide community stakeholders and researchers a broad spectrum of strategies for analysis. And ideally, INCORE will incorporate an extensive portfolio of decision possibilities and policy levers as relevant to specific communities. Some of these levers have already been implemented, such as retrofits, scheduling, and component enhancements, and others are currently in progress. The policy levers will be filtered through and combined with a community-specific profile with respect to their goals, internal capabilities, and resources, risk tolerances, long-term versus short-term outlook. This will feed the sophisticated decision algorithms that support the scale and complexity of the problems and handle the inherent uncertainty, the result of which will provide for a spectrum of optimal policy portfolios to meet community goals. For example, a policy strategy might be a combination of building retrofits, land use management, and financial incentives. The solution then can be evaluated with respect to their risk and potential impacts over time. In summary, good decisions must be based on community-specific goals, constraints, risk tolerance, and problem uncertainty. INCORE addresses both current resilience goals and the desired resilience goals, and provides a mechanism to explore the gaps between the status quo and aspirational levels. Currently, we are expanding the portfolio of policy levers to better support optimal policy strategies. At this time, I'd like to invite Dr. Elena Sutley from the University of Kansas to present on field studies and validation.
All right, thanks, Charles. Hi, everyone. As Charles mentioned, my name is Elena Sutley, and I'd like to talk to you today about supporting field studies and validation. The work I'm going to present is the collective work of about 30 different people, many of whom are in the room with us today, so I'm very grateful for the opportunity to present on our behalf. So let's start by discussing what validation means to the center. Validation is traditionally defined as the process of determining if a mathematical or computational model of an event represents the actual event with sufficient accuracy. It allows us to answer the question, are we solving the correct equations? This definition works great for engineers. We can compare model results to fundamental mathematical or physics-based relationships or design experiments for validation testing. But as you've seen in the last hour, the center is much more than just traditional engineering. We are working to develop models of very complex, interdependent, and multidisciplinary systems representing communities. Therefore, the traditional definition of validation presents challenges given that recovery takes many years for communities, and communities are unique. This means that designing an experiment is likely not possible, and collecting sufficient data takes significant time, and such data must assume large uncertainty in order to be generalized. The center is working to develop its own definition of validation that meets the needs of providing some level of a checking system that confirms our models are correctly reflecting the workings of a real-world process with sufficient uncertainty. I want to give you an update on where we are now in that process. So you've heard about each one of these already today, and so now I can speak about them collectively, but the center tests and validates its algorithms through testbeds, hindcast, and field studies. So here we have Centerville, we have Seaside, Oregon, the Memphis Metropolitan Statistical Area in Tennessee, we have Galveston, Texas, Joplin, Missouri, and Lumberton, North Carolina, where Centerville is a virtual community designed for algorithm testing, and the other 5 are real communities in the United States. And so collectively, these 6 make up our testbeds, hindcast, and field studies, where different algorithms use these different sites differently. Here's one example of how testbeds, field studies, and hindcasts are used to support INCORE modeling. For example, we start with the need of a predictive resilience model. We use empirical studies, systematic literature reviews, and field studies to inform the process-based predictive resilience model. We use testbeds to test and calibrate the models, and we use hindcasts to validate those models. A specific example that I'm showing here is of our housing recovery model. So where we are using Galveston to inform, Lumberton to calibrate and refine, and then we're using Joplin for validation. We use different models, or different models use the different sites for informing, testing, and validating, but never use the same location to both inform or calibrate and validate. I'd like to share a little bit with you about Joplin, Galveston, and Lumberton. You've heard us talk about all of these before. I won't spend much time on these, but the purpose of the Galveston study was to focus on a hurricane scenario, specifically 2008 Hurricane Ike. To develop Tier 1 and Tier 2 research tools, where depending on the amount of input data a user of NCORE might have, they might choose to use the Tier 1 or the Tier 2 models, and where the uncertainty and computational time adjust accordingly, like you heard earlier. The Galveston study allows us to refine and integrate hurricane hazard models on wind and surge with interdependent infrastructure, including electric power, water, telecommunication, and transportation network models. And as the previous flow diagram of housing recovery showed, we're using Galveston for a data-driven housing recovery model to inform our predictive model on what factors prove significant in predicting specific housing recovery indicators. Galveston's being used in other modeling efforts as well, as you've heard in the past hour, including the business recovery modeling. Next is Joplin, where the purpose is to focus on a tornado scenario, specifically the 2011 EF5 multi-vortex tornado. The center is using Joplin to calibrate or validate various algorithms with interdependencies, including validating the housing recovery model I showed a few slides back, and a damage repair model that I'd like to show you now. But first, to provide you with a quick overview of Joplin, the city has a population of approximately 51,000 people and 23,000 housing units. 8 years ago, or approximately 8 years ago, about a month shy of that, on May 22nd, 2011, a multi-vortex EF5 tornado ravaged the city, killing 161 people and injuring at least 1,150 people. This was the costliest, single most costliest tornado in U.S. history, with an estimated $2.8 billion in disaster losses. The image on the screen shows the tornado's path through the city of Joplin, where the dark red in the center depicts the area reaching EF5 wind speeds and the outermost blue area experiencing EF0 wind speeds. So approximately 5 years after the tornado, center researchers visited Joplin and documented physical repair progress and occupancy status. Our data was coupled with an ongoing data collection effort that started with initial damage and continued by capturing imagery of repair progress in the city each year after the event. That field study and data coupling have been used to validate a fully probabilistic spatiotemporal damage repair model. The probabilistic model consists of tornado damage fragility functions for 16 building archetypes, including residential and commercial buildings. This figure here depicts a damage analysis performed by center researchers, where this first image is of damage state 1, and you can see the different dots and different colors on the screen, where qualitatively you can assign minor damage to damage state 1. If I click again, it's showing damage state 2, so a different array of buildings are highlighted in some spaces. I click again to damage state 3, and you see other parcels light up. And then damage state 4, where this is the buildings that experienced complete destruction. So all 23,000 plus buildings in the city of Joplin were assigned damage repair functions, and the results were validated using the data collected after the 2011 tornado. So, as I mentioned about that data, annual imagery was collected using street view style cameras that attach to the top of a vehicle. The screenshot on the top right is from the camera. The video is logged along the blue path in the map below, with the red dot showing where the camera is located in real time. All of this data was obtained starting immediately after the tornado and each year for 5 years, shared with us from Dr. Andrew Curtis at Kent State. We've had the privilege to process the data in shapefile form and develop a method for validating repair progress and occupancy predictions. This process, including defining categories and subcategories for recovery progress or recovery states. Recovery time is defined here as the amount of time that passes before a building reaches recovery state 4, that in this case uses two recovery indicators of repair completion and reoccupancy. Each dot on the figure, as you can see here, each dot on the figure is a building footprint polygon, and we have the video imagery comparison for approximately 3,000 buildings in Joplin. And as the previous slide indicated, the work is ongoing to process all of that video imagery. We've gotten through the first 2 years and we'll continue on to get through the full 5 years of imagery that we have information on. So moving out of Joplin, we have our longitudinal field study of Lumberton, North Carolina. The purpose of this study is to focus on flood scenarios, integrate engineering and social science models by capturing damage, disruption, and recovery with community-level interdependencies of these processes taking place simultaneously for schools, housing, and businesses. So as Sarah mentioned earlier, we have the individual level data on schools. We have the individual level data on housing units and on individual businesses to get those high resolution models. We are also using Lumberton to validate field study processes such as sampling and data collection methodologies, and have been able to establish a feedback loop with the city of Lumberton. To provide you a brief overview of Lumberton, it's an inland city in Robeson County, North Carolina. It has a diverse population of approximately 21,000 people, and as many of you, especially in the room, know, it was catastrophically flooded in 2016 after Hurricane Matthew, and unfortunately again in 2018 after Hurricane Florence. This second flood enabled the center to extend its coverage to successive events that may be critical to understand in the face of climate change. The center has completed 4 waves of systematic data collection to date, where the last wave was just 2 weeks ago. The team successfully achieved a 75% completion in results for both our business and housing samples, so that was really excellent. Across each of these waves, through initial damage and recovery progress, the intersection of physical and social vulnerability has been observed and documented, and this too is critical for community-level resilience models for the center. Each wave has had different objectives, whether, to measure initial damage and disruption if it was immediately after the event, or to capture recovery progress if it was, say, a year later or 6 months later when we've gone back on these other visits. Additionally, between the last 2 systematic studies, we sent a smaller team in to capture real-time decision-making and the obtaining of recovery resources for the rebuilding of public housing. So when we do these data collection efforts, these field study waves in Lumberton, we capture interdependencies along the way through an innovative sampling methodology and ask our samples about utility outages, including water, wastewater, electric power, and telecommunication, as well as interdependencies across housing, business, and education sectors. All the while, we're documenting the availability and flow of external financial resources, measures of social vulnerability, and actions taken towards mitigation and preparedness. As you heard earlier, we ask people, why did you dislocate? Why did you continue to stay dislocated? What were the factors that you used to decide to return home? And similar questions for businesses. Similar to Joplin, but here specific to flood, we've also developed detailed probabilistic damage-based models using 25 archetypes and assigned them to all of the 20,000 plus buildings in Lumberton, as shown on these maps, where at any point you can zoom in, like I've done on the right, and see the detailed building footprint and building classification. In fact, many models are using the Lumberton data in different ways. With each wave, we're able to expand our scope to different center and NCORE needs. This slide provides a list of the models to date that are being informed by or validated by the Lumberton field study. I wish I had the time to go through all of these with you because they really are all exceptional work, but I'll share just one with you that's some very recent effort made by our business recovery team. So they are taking a stepwise Bayesian modeling approach to quantify business recovery using 4 indicators: interrupted operation days, revenue recovery, customer retention, and employee retention. There are 3 steps to the modeling process: data collection, developing the model, and then model selection. So you can see from the model flow diagram on the right. In the first step, an appropriate data set to calibrate the model is collected. Next, a set of initial candidate model forms containing the most important predictors of the measure of interest are developed. From there, each candidate model is upgraded by accounting for model diagnostics and elimination of inconclusive terms. And finally, the most desirable model is selected and high correlation between model parameters is eliminated. Looking at the flow diagram, you see several instances of input variables. So these input variables consist of 7 categories listed on the screen here and include direct and indirect impacts, business characteristics, and local context, for example. Housing recovery is also captured in the business recovery model through different approaches, and this is critical since businesses and housing recover interdependently. People need income to repair their homes, people need to be able to shelter somewhere to return to work, and people need to be living in the community to reestablish the local economy through purchasing goods and services. So you can see that the Lumberton Field Study itself has been very successful in collecting data, and many important models are being developed and validated thanks to that data. Only a small portion could be presented here, and so please download the NIST Special Publication 1230 to learn more about the first wave of the Lumberton Field Study, and look for the Wave 2 report to come out this summer. The Center will continue to refine its definition of validation with special attention to how validation affects decisions and is needed for strategic foresight to improve resilience. How do we know if right is right, and how right does it have to be? These are important questions that we are being very intentional about answering. We will have guides prepared for consistency and validation for NCORE users and contributors as we move forward as well. So thank you so much for your attention. I'll now pass to Zhang Li at NCSA for a demonstration of NCORE.
Thank you. This time I would like to show you a pre-recorded video clip of the NCORE currently developing very actively. Just for information, this is a kind of teaser of the preview we're going to release on later on this year. And some of the screenshots and some video clip may subject to change or improved later on. So this NCORE is a demo going to focus on more cyber infrastructures. So we have some architecture and components within the NCORE system. It's built on the cloud computing system, Kubernetes and Docker, and we have these 4 important components. So the first is a PyNCORE Python library. They implement the NCORE analysis and some of the algorithms we developed and studied so far. And NCORE web services contains hazard service, data service, and semantic services, and fragility services. And then web tools going to be a lightweight web application that you are able to access those web services and database and behind. And NCORE Lab is a customized Jupyter Lab, Jupyter Hub environment that you are able to access 3 components you are seeing right now. So I'm going to show some of the demo, but in general, there are 2 ways to use the NCORE right now. One is in the online, you could log into the NCORE Lab. You are able to access all those components I just mentioned to you. Or you can access those services and those components on your local machine. So this time I'm going to show you the NCORE Lab. You are able to play and access all those components. So now you log into the NCORE Lab, and you will see this customized NCORE Lab, which is customized version of Jupyter Lab or Jupyter Hub. So you are able to see that some of the icons and some of the menu items is specifically for NCORE systems. So I'm going to show you some of the web tools within the NCORE Lab like this. So this is a fragility web application. It accesses the fragility database we have. You can filter different type of the hazard. You can also filter down to the different infrastructures, and you are able to search those fragility curve and identify which one you want to use. And also you can access the data service. The data application, data browser shows you different kind of data set. In this case, you see building inventory in the Shelby County data set. It provides preview and other metadata also. And also it allows you to access to some of the documentation. So in this case, you will see some analysis documentation, population dislocation analysis, for example, so detailed explanation, and also pointing to the papers based on this analysis. At the same time, it gives you the technical documentation of all the class definitions, method definitions, and all those things you need when you use the PyIncore, the Python library on your system. And then I'm going to show you two demos today. And one is the building damage analysis due to tsunami. So this screenshot currently shows the Jupyter Notebook that utilize all the services and PyIncore library. And then it shows that how to set up, how to run this analysis. And the first part is authentication. You need to connect to the service. Then you need to set up some of the data set and parameters. And now we're going to look at some of the tsunami data we're going to have. This is a predefined tsunami data around the seaside Oregon. You are able to also look at those data layers and zoom in and out, also turn on and off the layers within the Jupyter Notebook environment. Now I turned off the building, now turn on the building so you're able to see location and things like that. And using this hazard layer and also building inventory data, we're going to run a building damage analysis. So you are able to see here, I'm going to highlight the building damage class right here, that it connects to the service, but at the same time it has an algorithm behind it to query the fragility curve and look at the inventory data and compute the damage of the buildings due to tsunami. So you can see those are set up, and then you're able to run, and after that it generates the outputs. Now from here, when you play with these outputs, you are able to use very popular Python libraries. In this case, I'm using Pandas, one of the data analytics library, able to look at the data very quickly, to just look at the top 5 most damaged buildings and things like that. And then also using that information to quickly collect the statistical information of each column. In this case, I'm looking at the mean damage column, some of the statistical information very quickly computed here. And at the same time, you could actually visualize things very quickly. In this case, I'm visualizing mean damage and hazard value as a scatter plot. You could very quickly using this Pandas library also. And just also another way to visualize is distribution histogram with the mean damage. So this demonstration quickly shows you that Python library, which is PyIncore we develop, is not just for Incore, but because of we created the interface to the popular other Python libraries. So you are utilizing those libraries for your visualization or statistical analysis if you want to. And the next demo, also another part here is you can also able to access CSV file in Jupyter Lab. It actually shows some of the visualization very quickly. Second demo is dislocation population analysis. Especially this demo focus on chaining different analysis. You see already that there is a 4 analysis involved in, so these things are all feed into the population dislocation analysis to do this analysis can perform. So similarly, we do the authentication, and now we are trying to run the stochastic population allocation analysis first. You can see that, I'm sorry, I pressed the wrong button. So stochastic population allocation analysis also has the same class. And you may notice that we also allow them to set up some seed numbers and iteration number, which allow you to directly debugging some of the uncertainty analysis if you want to. Same way you can visualize the tables using the Pandas library and you can see number of people assigned to each building. And you can look at quickly about, there's about 41 buildings, and then how many people are assigned to each buildings like that. And after that, you can also look at some histogram of this distribution of this location. Now we're going to run the building damage analysis using the earthquake. So this case, we also predefined the seaside earthquake, and you can look at those earthquake definition. You are able to see a detailed definition of how we create earthquake. It's a magnitude is 7.0, and also depth is 10 kilometers, and the location nearby the seaside. And using that information, similarly, we are able to visualize these two layers of earthquake layer and also building layers. So same way you can zoom in and out to looking at your data set on this OpenStreetMap as a background data. After that, you are now running the building damage analysis. Note that this building damage analysis class is the same as previous one for the tsunami, which means that the same analysis, but now using different hazard and different building inventory data. And then algorithm already has a way to identify the proper fragility curve of each building. And now you can look at the mean damage of the buildings, and similarly look at some simple statistics of each columns. And also quickly visualize that histogram of the mean damage. Now we get into the population dislocation. We're going to plug in those chaining, this is the result of the previous analysis. First one is now we're chaining to building damage output from building damage analysis as an input to the population dislocation here. And second part is a stochastic allocation result into the population dislocation. Now we are able to run population dislocation analysis, and it produce the output like this, that it indicating that which building need to be dislocated, or those people in the building need to be dislocated, true and false. After that, also you are able to visualize this output using this library, like a pie chart this way. So this is the demonstration of so far the how to use InCore within the InCore lab. I'm going to quickly explain to you about how you could do the online on your local machine. We're going to give you access later when you release InCore. There will be a web page of this InCore landing page, which has all the pointing to this component I just explained to you and showed to you. So in this site, you are able to download the Python packages, also access to all this installation, documentation, and detailed documentation this page, and also access to the web service, and also it provides web service documentation. So if you have knowledge to how to use web services, this is documentation you can utilize and build your own services also. And InCore Lab and also web tools link will be available through this website, so you're able to access those things through this website and running from your local machines. So that's the end of my demo, and we believe that we're going to release the InCore and later this year, so you will access to all those components I showed to you. And next, I'm going to invite back to the Bruce, and you're going to talk about future of InCore.
Well, I hope you'll agree from what you've heard over the last hour and a quarter that InCore promises to be a really, truly remarkable computational environment for those interested in resilience, community resilience assessment and policy making. And before we go on to the question and answering session, I'd like to just share with you some thoughts about our thoughts about what comes next. And so some of the things we're working on right now are listed here. In our current work, we're moving toward measurement science implementation away from a creation in an effort to offer a research product that's useful to the maximum number of users. The basic research conducted over the first 4+ years will continue. However, the emphasis is going to shift a little bit toward implementation, and that shift will be guided by the structure of InCore, which you've learned about this morning. Some of the current implementation challenges that we're working with in developing InCore as an effective open source platform deal with interfacing the InCore modules, modeling interdependencies for very, very large complex systems, advanced recovery modeling. You can read some of the other challenges on this slide. I think the one that I would like to emphasize is the validation task, which I've listed last. I think that one's especially important because, as you've seen, INCOR is an extraordinarily complex and comprehensive computational environment, and it's important for the user community, whoever they may be, to have confidence in the results that it produces, either for understanding community resilience or actually for policy making. And so the validation portion of the exercise is something that we think is very important. Now, building for the future is something I think that has been on all of our minds, certainly those of us who are involved with managing the direction of the center research. And to build for the future, we need to build a constituency for the use of INCOR in resilience research, assessment, and for policy development. And this is by no means a comprehensive list, but some of the things that this is going to involve is building upon some of the collaborations that we've already established, as well as developing new collaborations in both the public and the private sectors by demonstrating the success of INCOR as a risk-informed decision tool. And of course, this is tied very closely to the validation portion of the current research program. And finally, to create educational programs to create an informed user community that will be anxious to incorporate INCOR in their own research and policy development type work. So these are some of the things that we're thinking about, ways of moving forward and accomplishing these goals. John early on let the cat out of the bag when he said that INCOR is scheduled for release in open source form in December of 2019. And between now and then, we hope that we can develop a community of users who will actually use INCOR in their own research and community risk management, both within the center as well as without the center. And I'll extend right now an invitation to people to contact us if they're interested in having more information as to how to do this. And so with that, I'd like to close by saying that what you've seen this morning is the effort of a very large team of very, very capable investigators and students and postdocs working together. And here are just a few of them. During the webinar this morning, we've received some questions, and Maria Dillard and Andre Barbosa and Connie Hale, I'm sitting here in the first row, and have been kind of tracking what's come in here and will assist with the question and answering period. So if you didn't get the contact information before, here it is again. And we welcome your questions. And thank you very much for taking the time to spend your morning with us and to learn something more about INCOR, a product that we're very, very excited about. So thank you very much.
So now as we transition to the public Q&A, we did receive quite a few questions, and I want to thank Connie and Maria for going through all these questions. I'll start off and answer this first question, and then I'll open it up, and we will have at least one question for econ, social sciences, and engineering, and then if time permits, we'll go back and have a second round. But the first one was, will the slides be available for download? Quite a few people, and I'll answer that one already and say that the presentation will remain up on YouTube for everybody, but the slides are not typically made available. However, please do contact the directors at the center, and it may be possible for specific questions. And John?
And if there's a particular few slides that somebody's interested in, certainly get in contact with that presenter or with Bruce or myself. This is John. and likely we can get you some of those slides.
Okay, so our first question is for the social science, some of the social scientists up there, but also John included in this, and is a broader question. How does INCOR deal with other parts of the community, such as educational institutions, government, healthcare, other things?
Why don't you start it?
Okay, I'll be happy to start that off. So one of the major efforts in our in our next few years is to look at the detailed models of the social institutions. So right now those we have basic models. We have actually a very detailed hospital network model that's not yet an INCOR that needs to be extended to be a whole health system model. Schools are being studied as well. There was one dissertation partially from the center that focused on schools within social science from Colorado State University just recently. So those are being looked at. We didn't present them directly today, but those will be some of those will be in the INCOR release in partial form. And then they'll be improved as the years go on. And of course, those out there asking that question have the ability to then contribute to the core and improve them even further.
Yeah, I would only just basically echo what John's saying, but also those have been important elements in the field work as well, too. Extensive work, especially in Lumberton, with schools and school system, schools and their recovery efforts, as well as the difficulties in funding those as well too. So those will be much more incorporated as we pass forward.
Move on to the second question, but I'll just say that, Walt, you just answered another question that there was for social sciences, which had to do with field data collection and methods and other things. So we'll leave it at that in the interest of time. The next question for econ, so Harvey, there was a question on what is the typical time step that is being used for these type of analysis?
Well, that's a great question. So the data we've collected is annual data. So usually there are annual outcomes that we're looking at, but we've developed a method, which we'll be talking about this afternoon, of how we can decompose annual outcomes into monthly time steps. So, and by changing elasticities and other behavioral equations. So it's a big deal because the recovery process could go month by month. So we have to decompose the annual outcomes. So that's a major focus of what we'll be doing in the future.
Thank you for that answer. On the engineering side, we have a question maybe for Paulo or Jamie, which is a little bit more in the weeds of things, but I think it's still worth asking. And the question goes like this: in a complex network such as the one that was shown here today, where you have water, electricity, and other networks, typically, there are a large number of minimum cut sets, so this gets really technical, but it may lead to a higher system risk, even though the intensity of the events may be small. So could you explain a little bit more about how the network analysis is being done, please?
It is a great question. As you said, there may be a little detail. So the connectivity is used to define the network topology first, which is then used in a flow analysis, and the flow analysis gives the state of functionality of each node in the network. So the cut sets and mean cut sets or link sets, if one wants to use that, can then be used to define the possible failure modes in a system reliability analysis, which then is the modeling of the uncertainty of the state of functionality of each node in the network. And this uncertainty propagation defines the probability of the state of functionality of each node, and then is part of ongoing work on the uncertainty propagation. More details about the general formulation and the specific analysis for Seaside, since that was part of the question, can be found in a book that we recently published that collects much of the work of the center, titled Radler's Handbook of Sustainable and Resilient Infrastructure.
Thank you, Paulo. I'm not sure everybody understood that. I'm sure I didn't, but please do ask Paulo for more. We have one more question.
Okay, Okay, some of our viewers today wanted to know, is there a reference, such as a manual, on all the implemented fragility functions that are in INCOR right now? Maybe John or Zhang could take care of this.
So currently, we recorded all the authors and relative to some papers on our database right now. So when the fragility curve database and web tools opened, you are able to see the metadata behind the fragility curves.
There's a live question which right here from YouTube, which is, can pre-event retrofits, countermeasure mitigation solutions be probabilistic and or deterministic, and how can those be incorporated in the analysis that's being done in INCOR?
With the Lumberton, the most recent wave of Lumberton data collection that we did, we have been asking households about very specific actions, mitigation actions that they have been taking as a result of the losses that they had from Hurricane Matthew, and to what extent, now we can see to what extent that contributed to reduction of damages that they could potentially have received from Hurricane Florence. So right now, with our Lumberton data, we are able to incorporate that household level mitigation data into our predictions of damage and predictions of recovery.
And just to complement Sarah's reply, going back to some of the fragility formulations and that large portfolio that Zhang was mentioning is referenceable within INCOR, there are many fragility functions that depict the impact of retrofit and how it potentially reduces that fragility when exposed to different hazards. And these are available within INCOR for a range of different components, such as bridges or buildings or other systems.
And if I could just say something, we've also done mitigation strategies in the CG model. So we've had a fixed amount of funds that we have available, so we can then retrofit, and Charles has done this, retrofit a series of buildings, then rerun the earthquake through, or the natural hazard, to look at the economic savings of the mitigation policy. So, and that's a big focus on what we'll be doing in the future.
Okay, lots of people presented and talked about interdependencies. So one question is, what was a surprising or highly important interdependency that you came across in your work that maybe hasn't been accounted for previously, but now is something that's being incorporated in the modeling? This could be for anybody that wants to respond.
Well, at least this is my answer, and there might be more to this. In the past, we often focused on dependencies and interdependencies within the different fields of expertise, within engineering systems only. So the part of the webinar that I presented, for example, we put together dependencies and interdependencies between engineering systems or infrastructure and social systems, and we're planning to do so also for the socioeconomic part. So the short answer is the dependency and interdependencies across the different fields is something that has not been done before, and I think is new that we're putting forward now.
Yeah, just to echo what Paolo said, I mean, it's really been fun to actually, rather than again simply a pass-through structure, to actually have a fully integrated structure. So the population, the vacancy status, and the like with respect to residences or housing units actually can be played in from the beginning, and not just simply taking the damage to actually look at dislocation. I think the other issue that certainly is there, and actually kind of comes from work of Yu Zhao and Shannon Van Zandt, and that is that linkage again between, as you saw, between households and businesses as well too, right? I mean, there's a chicken and egg kind of phenomena there. If we lose our population, what impacts the business? If we lose the businesses, what impacts that going to have on the population as well too? So I think we're moving in even further in that direction, and I think that's a really exciting linkage as well too. And one other final thing, and just to kind of echo again, Paolo, and that is, oftentimes in the behavioral work, we maybe focus on damage, but don't focus as much on infrastructure. And I think what we're seeing is really that linkage as well too. That's being played out.
Do you mind? Oh, I'm sorry.
This was a really good question because we all want to speak to it. One of the things that's been interesting and say somewhat unexpected that we've seen in the Lumberton data that you could classify in a way as an interdependency was in the data captured during wave 2. So this was January 2018, about 14 months after Hurricane Matthew when we went back to Lumberton. And so the data showed the longest dislocation times for people who had complete damage to their homes. That part makes sense. But the second longest dislocation times for people who actually experienced no damage to their homes. And so when we started looking at the intersection of the social vulnerability factors, the outages of utilities, as well as physical damage, it allowed us to see a picture that we didn't necessarily predict ahead of time.
Very similar to what Elena was just saying. So when you look at the interdependencies and you find that you have, when you have the cascading effects from this and loss of functionality in different networks, you have very non-intuitive patterns that come up, and different elements and subpopulations of your community are affected that you would not have necessarily seen. So some of the work we've done is look at vulnerability maps based upon not just the direct damage, but then the functionality loss. I think that Paulo has been working on something like that as well. One of the things that I'm interested in working with Harvey on is also looking at a better tie back and forth, the interdependency between the economic systems and the physical infrastructure systems. So a dependency both ways.
Yeah, and working with Charles, we've been running a scenario where we run 500 simulations, and then we look at how the outcomes are impacted by different aspects of the damages that the civil engineering team provides. And I've never pushed a CG model like this before. I've learned so much about this model in the Shelby County world that I never would have thought about the results we're getting if I hadn't been working with these people. So it's been great.
We'll use that as our last answer in the Q&A period, and I'll pass it back to John and Bruce to close out the webinar.
Okay, well, with that, we'd like to thank the online audience for attending, and please join me again in thanking all the speakers here live in the room. Thank you.